So can we have a warm welcome for Robin to the stage, please?
Yeah. So I'm going to talk to you a little bit about carbon budgets and how not to spend them. First of all, you're probably wondering what a carbon budget is, but before we talk about that, I'm going to talk to you a little bit about what global warming is and why we care about it. So hopefully everyone here has heard of global warming, you know it's a bad thing, but you might be wondering how bad is it, and when does it start getting really bad? Here you can see like a plot. This is from a recently published report by the IPCC about how different systems are affected by different temperatures. So here we've got temperatures. We're currently around 1.1 to 1.2 degrees above what we were in the 1850 to 1900, which we consider the baseline, because that's when we start getting decent temperature data. We're 1.1 to 1.2 degrees above that at the moment, so that's around here. And you can see that quite a lot of these things that you might measure the impact on, how many wildfires you see, loss of permafrost, loss of biodiversity, all of these are kind of orange at the moment. There's a few that haven't really started noticing climate change yet. Rocky shores, salt marshes, they're covered in water. It doesn't really matter to them very much about how warm they get if it's only a degree or two. But most things are already showing some signs of climate change, so you can just directly observe like the effects of climate change on most of these systems, dryland, tree mortality, carbon loss, etc. But things get quite a lot worse as you increase the temperature from 1 to 2 degrees, and then 2 to 3 to 4, things generally go downhill pretty rapidly. Different systems, however, are showing very different patterns with those temperatures. So although, like, if you own a kelp forest, you probably don't care too much about being at 1.1 or even 1.5 degrees. You probably really would hate it if you were to go above 2 or 3 degrees. By contrast, if you are a coral reef, you're already like really suffering very strongly by the time you get to 1.5 degrees. So the lesson you can take from like all of this plotted together is that like every 0.1 of a degree matters a lot to some system, but there is also no temperature at which like the entire world is going to die, right? So someone is going to like be alive in some system, even if you get to like absurdly high temperatures like 4 degrees, right? The deserts are not going to become completely deserty. They're just sort of used to it being deserty, right? So what this means is like when you're talking about human stuff, you've always got some sort of trade-off going on between like how much you spend adapting to climate change, like installing aircon, like moving money around, trying to find types of plants that will still grow in different temperatures, versus like actually stopping climate change. And that's fundamentally a political question. I'm here in the physics contingent, so my job is to not answer the political questions and just tell you about physics. So how can we get away from this political, like moral question about how we value different types of animals, how we value like human life, how we like value money, and just talk about like the interesting thing, which is numbers and maths. And that's going to be by means of a carbon budget. So at the moment, you might say we've got this thing called the Paris Agreement, where politicians came together and said we would like to aim for 1.5 degrees of global warming, as in like, when I say aim for, I don't mean that's the upper bar, I mean that's the, that is the like reasonable attempt made to stay below that. But we would definitely like to be well below 2 degrees. So for most of this conversation, like 1.5 and 2 degrees are the sort of target numbers. That is not historically what we have like been projecting. Like until fairly recently, we were projecting temperatures above 3 degrees. The last couple of COPs have actually, the climate change conference has been quite successful in bringing that down into just over 1 to 2 point something degree range in terms of if every government does exactly what they say they'll do, what will the temperature be? So you can have the really optimistic scenario where every government does exactly what it says, and we interpret their offers in the best possible light, and maybe we'll actually be compatible with the Paris Agreement already. More realistically, we're hovering around that 2 degree like temperature stage, which is not Paris compliant. Like we said, well below 2 degrees. So like 2 degrees is still a Paris fail, and you know there's uncertainty in exactly what temperature you reach. But more realistically, if governments don't do what they say they'll do, we're still talking above 2 degrees, but we're not talking like the 2-point-something degrees. So there's like some good news in terms of political action, mostly quite recently. But how can we translate this into like the actual things governments need to do? There's a trick, it turns out, when you look at how different climate models and also historically how we've emitted carbon. So here we've got cumulative carbon emissions since 1870 in this plot, and this is the relative temperature. And you'll notice that this is a curiously straight line. There is not a particularly good physical reason why this should be a straight line. There are some physical reasons why you'd expect this to curve down. There's several other physical reasons why you'd expect this to curve up. Those two things seem to be pretty much in balance if you look at history, and also if you look at a whole range of differently set up climate models. So all of the spots here come from unrelated climate models, or at least distantly related climate models. And basically, if you want to make a physically tractable climate model, you always discover that this relationship is at least proximately straight for the first couple of degrees. Sometimes they curve down after that. This is quite an interesting result. What this means is, if I only know what cumulative emissions were, in whatever the scenario, I can have at least a good approximation to what the temperature is going to be. In other words, we can frame this as a simple equation. Warming is proportional to cumulative CO2 emissions times a constant. The constant is known as TCRE. And you'll notice that these models do not agree on what TCRE is, but they all agree it's in this sort of range. If climate change wasn't real, by the way, then there would be some models that were like down here, which is just outside of the range of reasonable possibilities. But we can't tell whether it's like this or like this. Just depends on exactly which model we use. So this gives us some uncertainty in TCRE, which we can compare to historical measurements and use this to constrain what it might be reasonable numbers for it. Now, this is really useful because it means we can look only at what, like, we don't need to care about when carbon is emitted, we just need to care about how much carbon is emitted total across all times. And it gives us a yardstick to measure progress. Another sort of thing that this is actually quite handy for is it draws attention to the net zero as a target, right? Up until like a couple of decades ago, people often talked about climate action as reducing your emissions. If you know that you keep warming up as long as you're putting more carbon into the atmosphere, well, reducing your emissions doesn't stop you warming, right? You just warm more slowly. Now you need to get emissions to net zero. So that's just a direct insight from this. And you can use this then to set up this target whereby politicians, social scientists, biologists, whoever it is that has interests in, you know, people being alive, animals, et cetera, comes together to determine how much warming they think is okay. Physicists then translate this into carbon limits, and then we can give this over to politicians, people who are, you know, running the economy, to work out how to stay in these limits. And then you might feed that back and say, oh, wait, no, we could do a lot better than this. Now we think about it. It turns out to be much easier. And then we can go around and maybe come up with lower temperature limits. So in terms of like the actual maths that's needed to put this together, we've heard this term, TCRE. So let's take our current temperature. We've got a target temperature. But there's a couple of other annoying factors. I've only talked about CO2, but there's actually a few other things going on in the system, right? You might have heard of methane, you might have heard of N2O. There are a few other gases that we release that also cause warming. We need to take account of that somehow. And then there's this annoying possibility that after you get to net zero, things will keep heating up. So historically, people have talked a lot about permafrost melting and all these sort of feedback systems. There's some good news on this plot, by the way. The different models disagree on how much warming we get after net zero, but it's approximately zero. Some models actually suggest that after you get to net zero, you experience cooling, even if you don't release negative emissions. But approximately, we're looking at there being zero warming after you reach net zero. So like when you get to net zero of all greenhouse gases, you're done. It's fine. You don't need to sort of keep going. However, in practice, probably you're going to be emitting methane and other types of greenhouse gases. You will need to take out some carbon to counteract those. But looks like this term, warming after net zero, is at least very small, and non-CO2 warming is at least smaller than the CO2 warming that we're giving you at the moment. So all of these terms have some uncertainty in them, but we can include that uncertainty when we make physical models. We're only talking about warming until the end of the century, so like very slow warmings, like the complete loss of glaciers in, for instance, the entire of Antarctica. Hopefully that'll take more than a century to complete. So that would not be included in this model. But we do include like relatively fast warming effects in this model. So what do we get as our answers? Starting this year, as in like from January, we would have around 250 gigatons of CO2 for a 50% chance of staying below 1.5 degrees. That is not very much. It's approximately 6 years of the amount that we emit this year. We are definitely not saying that we should continue for 6 years emitting the exact amount that you emit now and then suddenly stop, because it's very difficult to suddenly stop. So realistically, if you sort of plot a linear trend from the amount we emit now to net zero, that's a 12-year timescale to get to net zero. There's a lot of uncertainty in this. I'm giving you the 33 to 66% uncertainty, which is about 500 to about 50 gigatons of CO2. The reason I've chosen this is because it's like a reasonable window to give you an idea, but also it's because this way at least both these numbers are positive. Obviously I could have chosen a slightly higher uncertainty window, in which case it's not obvious that we have a positive budget to get you to below 1.5 degrees. Fortunately, that's not such a problem if you only have a 2-degree target. So we're relatively confident that no matter like what we do, if we stop now, you would be below 2 degrees. I've also converted this to like what this means in terms of British people, because I assume that a lot of the people here are British. Basically, the British person emits quite close to the mean emissions of the world, but not the median, because there's a lot of people who are like emitting very little, but some people emit quite a lot, like some countries emit quite a lot, which drags the mean up. So essentially that's also 6 years of our emissions. Here on this plot, we've got both the emissions from the UK territory and also a higher plot if you include the emissions that we like require other people to produce from us overseas. So if you include what are known as consumption emissions, you get a higher line. Both of these have been trending down recently, but they have not been trending down fast enough to meet the net zero target that you can see here, which I plotted in with that linear trend. So we've got a ways to go, but it is also worth bearing in mind that we are making progress on some of these targets. Yeah, so if you want to do only a 2 degrees target, you've got around 30 years of current emissions. Some people get a bit confused with these terms, so they'll talk about carbon budget, but what they mean is the total carbon emitted in a given year. That's a valid use of the term, that's seen in the literature. It's just a different thing compared to what we're talking about here. Some people also confuse carbon budget for meaning carbon footprint, which is like the amount that you personally are responsible for. These are not really the same concept. But you can use the concept of a fixed carbon budget to try and set your carbon footprint in context, right? So you can say, what does COVID mean compared to like the carbon budget that we have remaining? So during COVID, we saw a decrease of around 7% in terms of emissions for 1 year, maybe a small reduction in the next year, and then we're basically back to what you'd expect now if COVID hadn't happened. This is like less than 10 gigatons easily saved, and of course we lost some fraction of that year of climate action because people were doing things to help prevent people from dying of COVID rather than helping people not die from climate change. So in terms of like the grand scheme of things, like 1 or 2 years of very minor decreases in emissions, not really a big deal. The fact that the timescale for reaching net zero whilst maintaining carbon budget is around a decade means that a lot of the things people have traditionally focused on for climate action are overrated, right? So people have talked a lot about population control. That helps for end of century warming because you just generally assume that emissions correlate with the number of people, but there's not really very much time to do things about like the number of people living on Earth. So in terms of like immediate action, it's not really clear what you would do other than killing enormous numbers of people that would seriously influence like carbon budget in the yearly sense that would be relevant to the carbon footprint, to the like overall remaining carbon budget. And the importance of net zero means that like locked-in consumption is much more valuable than like just a yearly reduction like COVID. So like restraining yourself from going on holiday for 1 year is not really that useful compared to like some sort of long-term action that means that going on holiday like permanently is of lower emissions. A lot of these messages I think are relatively basic, but they really don't seem to have filtered into how the media like is talking about climate change, right? I personally am currently very annoyed by the sheer number of articles that I have found telling me what sort of vegan milk I should be drinking. Almost all of them seem to be rotating around the idea that I'm obsessed with whether or not almonds or oat milk are slightly better for the environment. The reality is that, like, all of these are massively better than dairy, but even dairy is only responsible for something like 3% of all greenhouse gas emissions. Now, 3% is worth mentioning. That's why I've given it, like, you know, at least a good half minute of this talk. However, like, when you convert that into a 6-year, 10-year trajectory towards net zero, you're talking about a few months. So, like, it's worth thinking about, but you need to, like, contextualize this as buying time to make the more systematic changes that will allow us to reach a permanent, sustainable, like, net zero emission lifestyle. Also, like, side point, but, like, I don't understand why people are always very obsessed with the level of water use that is involved in various different types of plant milk. Like, water is not restrained in the same way that climate change restrains the amount of CO2 you can emit before reaching temperature, right? Water is replenished on a yearly basis. You can move it around by pumping it. Yeah, I don't know. I just find these articles extremely annoying because they seem to be very obsessed with minor details of your life rather than actually trying to incite, like, real, genuine change in how, like, our society is energetically powering itself. Maybe land use would matter a bit if we thought that the land use freed up by not having cows there is going to become trees and therefore take carbon out of the atmosphere that way. But in general, it's not clear that that is what is going to happen to that land. So open question, kind of turning over to politics again. What actually does matter is this part of the plot here of different types of emissions that we have, almost all of which are from, like, fossil-fueled energy. So you can see on this plot the green stuff, which I think is the stuff that has more attention paid to it in the media, to do with agriculture, forestry, and generally green things, is about a quarter of the issue, but almost all of it is things to do with fossil fuels and how we power our economy. And so, like, changing from the fossil fuel-based infrastructure to renewable, nuclear, if you like it, or other, like, non-CO2-based frameworks for powering society is, like, the main thing that we need to accomplish on a decadal timescale to be consistent with any of these sort of carbon-based climate action targets. Okay, so that's basically my talk. Carbon budgets are this estimate of how much we can emit before we exceed a temperature. They're all very small for, like, the normal politically relevant targets. They demonstrate the importance of net zero, and we need to do, like, big things if we want to actually stay inside them. So at this point, I can take some questions, if there are any questions from the floor. Person, yes? Yeah.
Given that 3/4 of the pie was energy, in your opinion, as an expert in the field, what is your hopes to replacing that base load of energy? And do you think that nuclear is part of that answer, or EV, or whatever?
So before I did my current research, I spent my PhD is actually in the physics of solar cells. So I have something of a vested interest in saying that solar cells can solve a large fraction of this pie. But it is also true to say that we do not want a single thing. Like, this pie is not a single pie, right? This is coal, this is gas, this is different types of oil. This is various things that we've had centuries to try and get together. We will replace it with another pie with many different things working together. I think that the majority of that pie should be renewable energy because it's the thing that is increasing in effectiveness most rapidly. It's going down in price. It's modular, which means that you don't need to have large governmental structures in order to, like, implement a small amount of power to power yourself. That all being said, I am not in the anti-nuclear camp. I think some amount of nuclear power is helpful for when you build a grid. This is definitely a political question rather than a personal, like, this is not me speaking from the voice of science. It just seems to be that, like, having some amount of nuclear in the mix is quite useful. There are people talking about small modular reactors, where you try and get these, like, scaling laws of renewable energy combined with the consistency of nuclear power. But I have quite a lot of security concerns about modular reactors that I don't necessarily have with renewable energy. So, like, it's more of a political question than it is like a pure physics question. But in general, I would say that, like, mostly being based around renewable energy with some amount of more variable, like, voluntary types of power source, so that includes like biogas, that includes some amount of wood burning, that includes some nuclear, just to provide like insulation against when you see extreme variability in like levels of sunlight and levels of wind, would be quite useful. Yes.
I had a very brief follow-up on that.
Well, you can, but it won't necessarily be heard by people at home.
Right, okay. Doesn't matter.
You can ask in the break.
Yeah.
That's all right. Next question.
Yeah.
Apart from the focusing on emitting less CO2, is there lots of research done on removing some of the CO2? You mentioned planting trees. Are there other ways we could remove CO2 instead of emitting less CO2 or on top of emitting less CO2?
Yeah. So the question is about like what are the techniques for removing CO2 from the world? So trees are the most obvious example. There are several other ways that you can do this. One of the techniques is to plant trees and then burn them, but capture the smoke that comes out of them and then store that underground. There are techniques where you can just do a chemical process that reacts the carbon in the atmosphere with a type of rock that you can grind up, for instance, or with like an electrically generated system. There's an enormous list of different technical things you can do to like maybe grow seaweed. You can, there's a very, very long list of things you can do that will do this. Almost all of these very much in the like rudimentary stages of development, but you can see examples of them happening. Basically, you can do a whole bunch of things. You get some carbon, usually want it to be in liquid form, and then you can pump it deep underground, which is, of course, where it came from in the first place. Hope it will react with some rocks and stay down there. There's actually relatively good evidence that it usually does stay down there. More of the problem is that if it stays down there, then it reacts with the rocks, and then you can't pump any more down because it will get stuck. Which is not the problem you'd expect to have with pumping things underground. But unfortunately, almost all the times we do this so as to pump up more oil and gas, which rather defeats the purpose if you're trying to reduce the amount in the atmosphere. But it is working technology. It's currently very expensive. So it's very hard to see how that plus fossil fuels will ever outcompete renewable energy that is decreasing in price so rapidly. There's a question at the back.
Is there any argument that any of the climate change is not man-made, not caused or unprecedented?
Yeah, so we have good measurements of the different... Sorry, the question was, is there any argument that any fraction of climate change is not man-made? So there is a component of... I haven't shown you the graphs here, but if you look at a temperature plot over time, there are some wiggles on it. Those wiggles are usually not man-made. They're usually mostly volcanoes going off. In terms of the absolute warming that you see, if we go back to the first plot, here we go. In terms of these wiggles are mostly not man-made. This part here, there's a sort of hump here. That hump is probably mostly a volcano going off here. There are also sunspot cycles and things like that, which overwhelmingly just don't matter when you're talking about the amount of warming that you see here. So there certainly are like natural cycles and non-cyclical events like volcanoes going off, which emit these sulfates into the sky, which there cause a small amount of dimming of the world. This is accounted for in the models, but it is irrelevant compared to the amount of warming that we've seen over this timescale here. Yeah, there's a question finally.
Yeah, I was curious if you think that any form of geoengineering can increase our carbon budget.
So the question is, do I believe any form of geoengineering can increase our carbon budget? I guess I should start by having a brief talk about geoengineering. So geoengineering is when you try and do something to change how the world fundamentally works. And many people would define carbon removal technology, so when you try and suck carbon out of the sky doing rocks, as types of geoengineering. There are other types of geoengineering based on trying to increase the reflectivity of the world. So painting large areas white, putting mirrors in space. There's a type of sand you can scatter across the Arctic to make up for the fact that it's losing ice, and the sand will be reflective instead. Loads of these things. Almost all of these things will have some effect on weather patterns. So you might be able to reduce the total warming, but you will still change the pattern of weather. Some of these I think are relatively harmless. So like painting roofs white is pretty harmless. It's probably beneficial for people living in hot countries anyway. Like it's a good idea, why not do it? Painting mountains white has been attempted, so slightly larger scale. You have to look into whether the paint is good for the environment, but like fundamentally, like that's not an issue from a climate point of view. And in this case, what you're doing is really trying to reduce some of the feedback mechanisms, right? So At the moment, you have glaciers. As those glaciers melt, that increases the warming. But if we paint the place where the glaciers were white, that can decrease the feedback of glaciers melt, and therefore we warm up as from the lack of reflectivity. So generally, I would be in favor of relatively mild amounts of geoengineering. The main one that is suggested, which you may have guessed from me mentioning volcanoes, is injecting very large amounts of sulfur dioxide into the sky. So when volcanoes go off, they often emit very large amounts of this particular gas that then forms small particles and changes the way clouds work in the sky, increasing the reflectivity of clouds and causing more sunlight to scatter back into space. Generally speaking, you can do this and you'll reduce the temperature of the world, and it's not obvious that it's fatal. So sulfur dioxide does cause acid rain, but in the amounts that you usually have happening for this, it's not that everyone dies. So there was it's kind of bad for some fishes, but it's not the end of the world. So there's a reasonable question as to whether you might want to do this a little bit when we're around 1.5 degrees to prevent going over 1.5 degrees for a short period of time. The problem is, if you want this to keep going for many decades, you need to keep pumping the sulfur into the sky because it falls out as acid rain, as we've just discussed. This is generally going to permanently be increasing the acidity of the oceans. It's going to have all kinds of strange effects on the weather because the way it spreads out over the world is not even. So you have weird patterns in the weather. I think almost all of the experts I've spoken to are quite concerned by doing this, certainly for any length of time. Doing it for 10 years may be plausible. It's basically like having a convenient volcano. But committing ourselves to doing this so as to permanently increase the carbon budget is not really a good idea. If you're only doing it for 10 years, it doesn't increase the carbon budget. It's just stretching out the time you have to spend the carbon budget, because you still have to get to net zero anyway. Okay?
So we're establishing the threshold, but there are some scenarios in which everyone dies. Any more questions? Let's get a drink.